So this is the 13th session in the subject of digital communications, and in this session we are going to study the baseband binary receiver, which of course includes baseband binary demodulation. Now before starting with the baseband binary receiver directly, it will be useful if we compare the baseband analog receiver with the baseband digital receiver, and then we will go ahead. So let us do that first. So in order to do that comparison, let us first of all see what are the various processing blocks in the analog baseband receiver. The first thing, of course, you need is the amplifier, because any signal which travels along the transmission line will necessarily get attenuated. Therefore, you will always need to do amplification as the signal is received. So this is the first block. Then you require a filter, and the filter has two objectives. One is to remove the out of the band noise. See, understand, every signal will always occupy certain band spectrum, and if you want to preserve the nature of the waveform, then the filter must have a gain which is constant in that band spectrum. But out of that band spectrum, the signal doesn't reside. Therefore, you want to remove the out of the band noise by using a filter, which means that within the band the gain will be constant. Outside the band, ideally the gain will be zero. So let's just repeat that. The objective of the filter is twofold: to remove out of the band noise, and it must be designed to preserve the waveform. That means within the band spectrum the gain should be constant. Then you require one more filter. This is required if the channel has inadequate response. So the signal has a certain band spectrum, and if the channel does not have adequate response, then it will get distorted. In that case, what you require is an equalizer filter whose transfer function will be inverse to that of the channel. So because of the inadequate response of the channel, the signal will get distorted. However, the distortion can be removed by using an equalizer with an appropriate transfer function, which is simply inverse to that of the channel. So these are the three main components which will be required in the analog baseband receiver. Now, similar components are required in the baseband digital binary receiver, but the objectives are different. So let us study. Uh, so first one is of course the same, the objective is same, to overcome the attenuation in the line. So you require an amplifier just as you require the amplification in the analog receiver. Then you require a filter. Now this filter of course would be required to remove the out of the band noise as in the case of analog, but then it is not designed to preserve the waveform. Because in the binary receiver, digital binary receiver, your interest is in finding out whether S1T was transmitted or S2T was transmitted. Once you make the correct decision, it does not matter what is the nature of the received waveform. But in order to reduce the bit error probability, you would like to maximize the signal to noise ratio. So in this case, the filter is designed in such a fashion that it maximizes the SN ratio. And when SN ratio is maximum, then the detection will have less probability of error. And this filter is called as a matched filter. So understand that the design philosophy here is different compared to analog. In analog, the gain must be constant over the band spectrum. Here, you shape the frequency response of the filter in such a fashion that SN ratio is maximized. And when filter is designed in this fashion, it is called as a matched filter. We'll see the design soon. Then you again require one more filter as in the case of analog case, equalizer filter. But in this case, again, our objective is not to get the original waveform, but to reduce the inter-symbol interference, which we had mentioned in one of our earlier lectures. And inter-symbol interference simply means that the tail of the previous symbol can interfere with the detection of the current symbol. That is called as the inter-symbol interference. And the equalizer filter is so designed that the ISI is minimized. Okay. So these are the various blocks. Now we will pay more attention to the matched filter. Amplifiers, of course, all of us know what it is. We will now talk about the matched filter, and we will study how to achieve the matched filter, how to synthesize it. So transfer function of the matched filter. Design of any filter basically means that you must know how HF varies as a function of frequency, amplitude as well as phase. Now, it can be shown that the transfer function of the matched filter to maximize the SN ratio will depend on the spectral description of the signal itself. And that is the reason it is called as a matched filter. The frequency response is matched to the band spectrum of the signal itself. Okay. So, next couple of slides will show to you why this is so. So, we'll do the analysis for that. So let's say we have a matched filter here which gives us maximum SN ratio. The input consists of two components. ST is the signal part and WT is the noise part. RT is the total signal. Output signal we denote by ZT because the wave shape at the output will not necessarily be same as the input wave shape, and it is not required as long as you made the correct detection whether 1 was transmitted or 0 was transmitted. So the output is ZT, but this also contains two parts, the signal part which we call as AT now and the noise part which we call as NT. So the input is ST signal part, output is AT signal part. The input noise part is WT and the output noise part is NT. Now in our calculations we'll need to calculate HF. So we'll need to know what is the Fourier transform of ST itself. So suppose we call it as SF. SF is the Fourier transform of ST. And AF, which is the output from the filter, so its Fourier transform will be the product of the transfer function and the Fourier transform of the input signal. This comes from the study of signals and systems. So AF will be HF into SF. All right. Now, what we do is, in order to take the decision, we find out the value at the end of the bit time period. So this is evaluated at t equal to t. So you are interested in finding out z with t equal to capital T. So this is AT with t equal to capital T and NT. In short, we can simply write this as z equal to A plus N, realizing that A is the output value, is the value of the output signal at t equal to t, and this is the value of the noise signal at t equal to capital T, end of the bit time. Okay. Now signal power at t equal to t is A squared here. Now n at t equal to t is not known, it's a random noise. This is a value at t equal to t, but you cannot predict. However, what you can calculate is the average noise power, that is sigma n squared, that can be calculated by knowing the power spectral density of noise, and which is often known for thermal noise. It can be calculated. Again, you are referred to signals and systems. Anyway, so let us proceed. Understand what we are trying to do is to obtain the expression for S and N in terms of HF and SF, and then try to see for which value of HF, for which expression of HF this SN is maximized. Okay, so let us move ahead. AT is the Fourier inverse of the AF, and AF is HF into SF as we saw, and this is the definition of the Fourier inverse. So this is the expression for AT as a function of t. When you evaluate this, you will get a function of t, and that is your AT. So you calculate this at t equal to capital T. So AT is equal to A is the same expression, except that this small t is replaced by capital T. And then you calculate the average noise power. N0 by 2 is the power spectral density of noise. And this again comes from the study of signals and systems. So you multiply this mod of HF whole squared, integrate, you get your average noise power. and then you can calculate a squared, that is the signal power. So that is mod of this. We are interested only in power, so we take the mod of this and whole squared. So the signal to noise ratio is given by a squared divided by sigma n squared. So we substitute from here and we get this. So you can see that this signal to noise ratio is a function of HF for a given SF. So ST has a certain time domain expression and we are assuming that that is known, therefore SF is known. So S by N therefore now is a function of HF, and we will select HF in such a fashion that we get the maximum value of S by N. So this expression can be derived by using an inequality theorem called as a Schwarz inequality theorem. And once you get the expression for HF, that is the expression for HF for maximum S by N. So I am skipping these steps, but I'm just indicating the method by using Schwarz inequality theorem. You can get the expression for HF, and we will now simply see what is this expression. We'll directly look at it. HF for maximum Sn. This is the complex conjugate of the Fourier transform of the input signal, and this is of course phase shifted by this 2 pi ft. So this is the condition for maximum Sn. So you can see that HF depends on the frequency spectrum of the input signal. That is why this filter is called as a matched filter, matched to the signal. And once you insert this value into the expression for Sn, you will get the maximum value of S by N, and that is given by 2E by N0, where E is the energy of the signal, total energy of the signal, which can either be calculated in the frequency domain in this way, or it can also be calculated in the time domain. Whichever happens to be more convenient, you can calculate the total energy of the signal over the bit time period. So remember, S squared t is the normalized power. You integrate from 0 to t and you will get the total energy of the signal over the bit time period. So if this is known, the maximum S by N is given by 2E by N0. Alright. So that is the frequency domain expression for the filter, the matched filter. And we would like to see what is the time domain specification. That is simply the inverse of HF, that is the impulse response. So let us see that. HT is the Fourier inverse of this. And again, referring to signals and systems, you will get HT, which is inverted ST with delayed by T. So graphically this will become clear. Suppose your ST is like this, okay. It could have some other shape also, but in case ST is like this, S minus T is the time inverted like this, and then delayed by T seconds. So the whole thing is delayed by T seconds. So that is your impulse response of the matched filter. So like any other filter, the matched filter also can be specified in two ways. One by its transfer function, which is given by this expression within the brackets, and other by the impulse response, which is given by this expression. Once we understand this, we'll see one simpler method of implementing the matched filter. Understand, once you obtain the expression for HF, this is the expression, but you still have to design it. Okay, so that filter can be designed in the frequency domain. However, there is a equivalent way of designing this filter by looking at the time domain. That is where the impulse response comes in. So we'll look at it. We'll look at this derivation that we call as the correlation realization of the matched filter. So let's write the expression for ZT, which is the convolution of the input signal, which is RT, convolved with the impulse response. So this is the expression for the convolution. Again, I keep referring you to the signals and systems. So 0 to t r tau h t minus tau d tau. But ht for the matched filter is known, and that is s of t minus t. So this h t minus tau can be written like this, where t is replaced by t minus tau. So this is s of t minus tau d tau. Okay. So this is simply repetition of this 0 to t r tau st minus t plus tau d tau. Now we want to integrate this over bit time. So replace t by t. So integral becomes 0 to t. The output is z at t equal to t. And since t is equal to t, this will cancel and you will get r tau s tau d tau. So we have got an alternative expression for the output from the matched filter in terms of the time domain quantities. This is the input signal, which consists of signal plus noise, and this is the signal part itself. Now notice that tau is a dummy variable here, so I could have used any other variable here. For example, this could have been RT, ST, DT. So in order to obtain this ZT, what you require is one multiplier, multiplying the input signal by the replica of the signal which was transmitted, multiplier, and then integration over the symbol time period or the bit time period. So the correlation realization of the matched filter will look like this. A multiplier RT and ST are the two inputs to the multiplier. Then you integrate from 0 to t and you get your ZT. Okay. So with that, we are now ready to study. But before we study the complete receiver, let us ask this question. See, so far we had not talked about the two inputs. Understand that in a binary receiver, the incoming signal ST can be either S1T or S2T. So the natural question that arises is, do we require two matched filters, one for S1T and S2T? That is the question we want to answer. And the answer is that in some cases you will need, but in many cases a single filter will do. So those cases we are going to consider here, and let us discuss them. So I am just reiterating that question. Since input can be S1T or S2T, do we need two matched filters? And the answer is that in many cases you don't need it. For example, if you have antipodal signals, antipodal signal means if S1T is PT, then S2T is simply minus PT. Remember, polar signaling was a case, one example of this, where our PT was a rectangular pulse, but it need not be rectangular. But as long as S2T is negative of this PT, it's an antipodal signal. So since the waveform is same, only the sign is different, so the matched filter required is only one. So a single filter matched to PT will do the job. Only thing that will happen is if S1T is received, the output of the matched filter will be positive, and when S2T is received, it will be negative. But you require a single matched filter. Again, if you consider on-off signaling, S1T is positive pulse and S2T is 0. So you don't need any matched filter for this. You require only one filter. And also for bipolar signaling, only a single filter will do the job. Okay. So let us now look at the complete baseband demodulator. So RT plus NT, that is the received signal. So this the incoming signal can be either S1T or S2T. Understand this RT is the summation of either S1T and NT or S2T and NT. Then you have a receiving filter, which is the matched filter we said. Then you have the equalizer filter. You sample the output at t equal to t and do the threshold comparison, and this is the estimate of the bit that you get. So mi dash. So this mi can be either, mi dash can be representing either S1T or S2T. So that is an estimate. So if the error correction is used, then it is the estimate of the coded bit. That is obvious. Okay. So now, as far as this session is concerned, we have more or less covered everything. So we'll just point out what we intend to do in the next session. So goals of the analysis for the following session are: find out the threshold to minimize the probability of error. Remember, let's look at that thing again. You require a threshold comparison at this point. So we'd like to know what should be the threshold, and that we want to calculate. So in the next session, we'll do our analysis in order to find the threshold to minimize the probability of error and then find out the error probability. That is what we are going to do. So in this session, we have seen what are the various blocks for the binary demodulation or binary receiver. We have studied what is a matched filter, what is its transfer function, what is its impulse response, and therefore how matched filter can also be realized by a correlator detector. And that's all in this session.